Okay, in this podcast, we're going to consider some of the structure and bonding aspects of alcohols and consequent properties of alcohols as we modify functional groups within the alcohol structure. First off, we're going to revisit the structure and bonding in water, just to remind you that really alcohols are just alkyl or organic derivatives of water. So it's very easy to use the water structure that we looked at constructing in an earlier podcast and modifying that structure to consider how an alkyl group bonds to the functional group OH. So here we go. We're going to just sketch out and look in a little more detail at the structure of methanol as an example, and this is to really explain how carbon links to the oxygen and replaces a hydrogen from water to form the methanol structure. So first of all, I'm just sketching out the rough lines of the methanol structure that I want to draw around, and just sort of positioning the hydrogens. And here we go. We're now looking at the particular hybrid orbitals that occur on carbon and oxygen. These are sp3 hybrids. sp3 hybrids you may have met before with structure and bonding in methane. If you haven't met sp3 hybrids, then you ought to look at the structure and bonding of methane in a textbook or certainly online. Okay, so these sp3 hybrids allow the bonding between a carbon and oxygen and hydrogen, and they're also going to lead to positions for the lone pairs. So the lone pairs of electrons on oxygen reside in an sp3 hybrid. When two hybrid orbitals overlap, this resultant bond, which is a covalent bond, is known as a sigma bond. The term sigma comes from the sort of symmetry of the bond, which is an axial symmetry, something you don't have to worry too much about. But these sigma bonds are created by overlap of orbitals. We've now introduced a carbon-oxygen covalent bond into the structure of water between the methyl substituent and the oxygen of water. There it is. And now we have methanol. Okay, let's consider the properties of methanol. And when you think about the properties of alcohols, you should also bear in mind the properties of water: boiling point, solubility aspects, states of water, and so on, because most of these apply to alcohols. Okay, in methanol, we've still got the dipolar aspect of the OH bond that was present in water, so that means that two molecules of methanol can hydrogen bond. And here we go. There's a hydrogen bond between the delta negative oxygen and delta positive hydrogen on another methanol. And this network can carry throughout a collection of methanol molecules, just like it did in the water hydrogen bonding network that we met in an earlier podcast. So here's methanol, and methanol is a liquid at room temperature and pressure. It's a low boiling liquid. Its boiling point is actually lower than water, and you might want to think why that might be the case. If we look at a family of alcohols, we can have a methanol, ethanol, and then we can extend the chain to further length alcohols, where N is a number 0 to anything you like, really, 10, 12, something like that. Let's consider water solubility. So think what we've done with those particular examples. The R group has changed from methyl to ethyl, and if we select a particular N for a chain, say 7, this would be now an octyl substituent, so that would be 1, 2 and 8 in terms of the length of the chain connected to the OH group. Methanol and water are mutually soluble, and that means that methanol can dissolve within water and water can dissolve in methanol if you pour the two liquids together, and this is also the case with ethanol. What this means is that really the small alkyl group is not having too much of a drastic effect on how these two molecules mix together. However, as you increase the length of the alkyl chain to 8, now the two molecules are not soluble. So octanol has little solubility in water and vice versa. And that's because we've introduced another dimension. The other dimension is now this, that we've got long alkyl chains. I'm just checking that I've got the right number of carbons. This is how we would draw octanol quickly. Now, octanol, because of this long alkyl chain, and working on the principle that like attracts like, the alkyl chains have now a affinity to one another because they don't like to be in water. They do like to be next to one another. These chains aggregate, and that network can carry on within the bulk of octanol, and that's one of the reasons why octanol's boiling point is greater than methanol. Notice that the hydrogen bonding situation in between octanol and methanol wouldn't change particularly much, but certainly the length of the alkyl chain, which causes octanol to be higher boiling, does change. So what you have in these chains is many small favourable non-bonding interactions. They come about because of van der Waals interactions. And if we consider what would happen in the bulk liquid, so here we have a beaker, albeit slightly badly drawn. I'll just tidy that up a little bit. Don't worry too much about it. So here we have a beaker, and we're considering the bulk properties of a mixture of an alcohol with a longer chain than methyl and ethyl, and considerably longer in the case of octanol. I'll just shorten the octanol chain to R, where R is C8. And we consider the properties between water and octanol. The partition occurs cleanly, in other words, the two materials separate.